Okay, in this video we're going to discuss how to graph a derivative. So if you have the function, then graphing the derivative shouldn't be hard as if you can find derivatives, right? So if I know the function is something like f of x equals x cubed, then I know the derivative f prime of x is 3x squared, and I could graph that. However, if I don't know the actual equation for my function, I can still come up with a rough sketch of its derivative by thinking about what the slopes of the tangent lines are at each of the x coordinates of my graph. So what we're going to do here is we're going to look at some graphs. So this is going to be a graph f of x. And instead of making like an xy table, so I could very easily make an xy table for these points on this graph. Instead of making an xy table, I'm going to make an x comma f prime of x table. So what that means is, at each of these x values on this graph, I want to write not what is the y coordinate there. I want to write what is the slope of the tangent line at that x coordinate. Okay, so I'm going to start with some that are pretty easy that I would suggest you always start with, and then you're going to have to kind of make some judgment calls as you go on through some of these. But again, I'll give you some hints on how to fill that in. So the places that I would start are at the x coordinates where you have a peak or a value, a local max or a local min is what those are called. So right here at an x coordinate of -2, this graph f of x kind of tops out there. So we have a local maximum there. So the slope of the tangent line there, if I were to draw a tangent line, that slope would be 0. So at -2, f prime of x is going to be 0. That also happens at +1. Down here we have a local minimum at +1. So at +1 it's going to be 0. And then kind of close to +3, right? So it's slightly to the left of +3. But pretty close to +3, it's going to be 0. So I'm going to put 0 here, even though I know it's actually not quite at 3. It's pretty close to 3 where it does that again. Okay. Now what that tells you about your function, or the graph of your derivative of your function, is that at -2, at 1, and at 3, your derivative will cross the x-axis. The y-coordinate of your derivative is what you got for the slope of your tangent line of your original function. Okay? So because the slope of the tangent line at -2 is 0, the y-coordinate of your derivative will be 0. And same is true at 1 and at 3. Now we actually know this is a little bit less than 3, so I'm actually going to put it just a little bit to the left of 3. But I know that my derivative is going to cross the x-axis at those 3 locations because the original function had a slope of 0. The tangent line had a slope of 0 to the original function at those x coordinates. Okay. So now what I'm going to do is I'm going to go through and kind of estimate what the rest of these would be. So I'm just going to draw these little line segments that I've been drawing and try to estimate about what that slope would be. A good tip is to have maybe like a pencil or something handy that you could lay down and kind of try to calculate the slope of that so you can extend that out a little bit. But I don't want to draw a ton of lines all over this in order to see that. So at -5, so that is right here. What is the slope of my tangent line? If I were to draw a tangent line here, about what slope would that line have? So if I extended that line segment out, I see that it looks like a slope of about 2, right? And again, sometimes you're going to have to make some judgment calls. At -4, the slope here, still a little bit steeper than 1, but not as steep as it was before, so I'm going to say 1.5. At -3, this looks like about a slope of 1 if I were to extend that out, so I'm going to put 1 here. At -1, my slope here at -1 appears to be about -1. And at 0, the slope of my tangent is about the same as it was for -1, so I'm going to say -1 as well. We already have 1 at 2. My slope here now, that's pretty flat. It's flatter than what I put for -3. So at -3, I said that was a slope of about 1. If I were to extend that out, it would kind of go through the corners of a box here. This is definitely flatter than that. So I'm going to say 1/2 for 2. At 4, that appears to be about -1. And then at 5, it's kind of hard to tell what's going on at 5, so I'm actually not going to fill that in. Now again, what I'm going to do at this point, I'm going to make these a different color. I'm going to go through and every place, starting with those places where it was 0, those are the easy ones to plot. But what I'm going to do is I'm going to plot these as coordinate points now. So -5, 2, and -4, 1.5. -3, 1. -1, -1, and 0, -1. See, we have 1, 0, 2, 1/2, 3, 0, 4, -1. Now again, these are supposed to be kind of smooth curves, right? So what I'm going to do is, I'm actually going to bring this up a little bit, but this is supposed to be a nice smooth curve. That would look something like that. And that would be the graph of my derivative f prime of x, okay, given that the first one was f of x. Okay, so it's kind of a difficult task, and the key is being able to make some good educated guesses on what those slopes would be, because it's kind of hard to see that. In just a minute, I'm going to go to Desmos and show you something I've created there to help with that, where you can type a function in and kind of see what the derivative is doing, what the slope looks like if we extend that out. But that's the idea there, plotting those slopes of tangent lines as y-coordinates. Okay, so I'm going to scroll down and answer some of these questions, and then hopefully that will help explain this a little bit better. So it says, what do you notice about the y value of the graph of the derivative when the function reaches a relative maximum? So a relative maximum is this place here where we get to the top where it maxes out. What did you notice about the y value of the graph of the derivative when it reaches a relative maximum? Well, it was 0. And the same for the next question. What do you notice about the y value of the graph of the derivative when the function reaches a relative minimum? That is also 0. What do you notice about the y values of the graph of the derivative when the function is increasing? So if the graph itself, if f of x is increasing, the graph is going up, what do I notice about the y values of the derivative? What you should notice is if a graph is increasing, all of those tangent line slopes will be positive, which means the y-coordinates for your derivative should be positive values. They should be above the y-axis. Every time that your graph is increasing, the y values of my derivative should be positive values. So I'm just going to put that they're positive. What do you notice about the y values of the graph of the derivative when the function is decreasing? Well, just the opposite. If my graph is decreasing, then my tangent line slopes are negative, so my y values of my derivative should be negative values. Okay, so hopefully that kind of makes sense. And what I would do when I go through this is I start with the places where it's 0, and then I also think to myself, at places where it's not 0, I say, is the tangent line positive or negative, and is it steep or is it somewhat flat? If it's a steep positive slope, that means that my y value is a big positive y value, so it should be a higher y value. If it's positive but not as steep, then it's a much lower y value but still positive, so it should still be above the x-axis. And then I go through that same thing with if the slope is negative. I think, well, is it a big negative or is it a small negative number? So let me show you in Desmos something I've created here. So we have a function, and I'm just using x cubed. So this is my original function. I'm going to put on here a point that I can move that just follows this function. So if I just move this slider, it's going to move that point along the graph. But then I've also written here in point slope form, this would be the equation of the tangent line given whatever a would be. So if I graph that, this would help as you drag this point along kind of estimate what the slopes of that would be. Right? So here it's a really steep. It's going to get steeper and steeper and steeper. So my derivative should be a really positive y value at that point in time. But if I bring it back this way, it's getting a still positive slope, but it's less and less and less until it becomes 0. And then here, again, it's positive, but flat, but it's going to get steeper as I go to the left. So I'm going to keep this up here, and then I'm going to show you what the derivative of this would be. So I'm going to put another graph on here that's y equals f prime of x. Now you should know that the equation for y equals f prime of x for this function would be 3x squared. So if I graph this, that is actually 3x squared. Okay? But notice when your original function was at 0, when your original function had a slope of 0, the derivative had a y value of 0. And then it's positive to the right, a smaller positive, but then increasingly more and more positive. And then over here, it's also positive, small positive, but if I go further to the left, increasingly more and more positive. Okay, you can change this function around. So let's say I put minus x squared plus 4x, and I kind of zoom out so I can see what's going on here. But it's kind of the same idea. Right? As I follow this point along my original function, I can track what the slopes of those tangent lines are, and I can plot those as x values. Okay, I'm going to make this a little bit more exaggerated here, and then kind of move this around so we can see. Okay, so my original function again is the red one, my derivative is the blue one. But here's one where I can tell, okay, it's very steep positive, less and less positive, less and less positive. Here it should be 0, so my derivative should be crossing the x-axis at that point, which it is. My derivative is a blue graph. Here it's becoming negative, negative, negative. Look at my derivative, it's a negative value. It reaches the most negative right about here. That's about as steep as this tangent line will get, and my derivative bottoms out there. That's as much negative as your tangent line slope will be. And then it becomes less and less negative. It's still negative, but it's becoming closer to 0 until it's 0 again here, which means my derivative should be crossing the x-axis right about there, which it is, and then it becomes really positive, so your derivative becomes more and more positive. Okay, so being able to edit that function to see what the derivative would look like. I also put on here the second derivative, which if I followed this blue line, this blue graph, I should be able to see what that would look like. It would actually just be a line in that case. And that should make sense because if your original function is a cubic function, your derivative would be a quadratic, and your second derivative would be a linear function. If you track that, hopefully that helps to make sense of that, tracking the slope of your tangent line to see what your derivative graph looks like.